Okay, so this is the review session for EGME 441 for midterm 1. Okay, so I looked at the poll this morning and I found that the overwhelming topic that you want me to cover is static biomechanical analysis. And so what I'm guessing is that everyone will just want to see a couple more examples and maybe redo some homework problems. So that's exactly what I'm going to do. And so I'm going to go through, I plan to go at least through 2 problems. I'm going to go through them in really careful detail, just so that you can kind of see, kind of once again, my thought process in doing these problems, how to compute the moment arms, how to compute, the equilibrium equations, and just so that you can kind of get some practice doing these one more time. Okay, so let's go ahead and begin. Okay, so I'm going to start with a problem from homework 2. Okay, and so I'm going to do homework 2, problem 3C. And so this is the overhead press problem from from that homework assignment. Okay, so I picked this one because I think this is a very good, kind of very typical kind of problem with kind of a lot of normal stuff kind of going on. And so it's good to kind of cover this. Okay, and so the context for this problem is that we want to do an analysis on someone doing an overhead press exercise. Okay, and so And so this is an analysis, of course, of the upper extremity. And so we're looking at the arms and, in this case, the shoulder as well. Okay. And so this is a 2-segment type of analysis. And so we have, we'll say this is the upper arm right here. Okay. And that's down there is the shoulder joint. And then we have another segment of the arm. So this is the lower arm right here. Okay. And then to represent the barbell or to represent the weight that the person is carrying, we'll have a weight of W up top here. Okay. Okay. And so let's go ahead and analyze this. And so we have our muscle force here. Okay. And that's angled with respect to the arm. And so the angle we're given there is theta m. In addition to that, we have our joint reaction forces. And so, unfortunately, they got cut off a little bit here. So we have Jx, Jy, okay, as we typically do. Next, we have the angles of the arms. Okay, so the arms are angled with respect to the horizontal. Okay, so that's going to be key right there. And so they're angled with respect to the horizontal given by angles theta 1, theta 2. Okay. We also have the lengths of the arms. And so we know that the upper arm segment here has a length of L1. The lower arm segment, or your forearm, has a length of L2. And then finally, the last thing that we have are the weights of the arms, as well as the weight at the end. Okay. And so we say the upper arm has a weight going downwards of W1. The weight of the lower arm has a weight of W2. And of course, the weight at the end of the arm has a weight of W. Okay. And so the values of all these parameters are given here. Okay, so let me go ahead and write them all down. So we'll say W has a value of 750 newtons. W1 has a value of 50 newtons. W2 has a value of 35 newtons. L1 has a value of 32 centimeters. L2 has a value of 37 centimeters. Theta 1 is 45 degrees. Theta 2 is 55 degrees. LM is 6 centimeters. I forgot to draw LM here. So LM is this distance right here. Okay. And theta M is 25 degrees. Okay. So, of course, you probably all know this at this point, but, for a lot of these problems, there's, a lot of parameters kind of going on. And so it's important to kind of stay organized, just that where to put the numbers where, okay? Especially in a problem like this where you have, several weights or several forces going on, and, there's lots of lengths and a lot of angles. And so, making sure you stay organized, I think, is the first step to making sure that you can do these problems on the exam, okay? Because on the exam, you're not only, trying to do the problems, but you're also trying to, make sure you finish it within the time allotted. And so, even though, it may be a bit difficult, but, taking that extra couple of minutes in the beginning to kind of organize all the information in the problem will kind of help you, stay organized throughout and end up saving you time, overall. Okay. All right. And so just like, most problems of this type, what we're interested in is computing the muscle force as well as the joint reaction forces. Okay. All right. And so we have three unknowns here. And so we're going to need our three equilibrium equations. And just like we typically do, we're going to start by summing the moments around the joint. Okay. So remember, the reason we do this is that, two of our three unknowns here, Jx and Jy, they're physically located at the same spot. And so we can take advantage of this. And so if we sum the moments around that point, then we know that Jx and Jy are not going to contribute to our moment equation, okay? Okay. And so that's basically the primary reason why we do that, is to kind of make our lives a bit easier. And so if we sum up the moments around that joint, then our resulting equation is only going to have one unknown, and that one unknown is the muscle force. And then we can solve that equation directly for that muscle force. Okay. Okay, so let's go ahead and sum the moments around the joint. All right. And so we know from the figure that except for the joint reaction forces, all the other forces here are going to contribute to that moment. And so in this case, we have four other forces. And so we have the muscle force, we have the weights of the two segments of the arm, as well as the weight at the end. And so we're going to have four components here. Okay. And remember, when you're forming the terms in the moment equation, you have to make a product. And so the product is going to be the magnitude of the force okay. And so all those are given to us here in the problem. And then the tricky part is that you're going to multiply it by the perpendicular distance between the force and the joint, which is known as the moment arm. And so I think that's the part that people get tripped up on the most, is determining what that moment arm is for every single force. Okay. Okay. So I'm going to start with the weights actually, and so we'll do the muscle force after that. And so I'm going to start with the weights because one thing that weights always have in common is that they're always vertical forces. Okay. Okay, let me give myself a bit more room because I want to write this tip. Okay. And so that's important because if we know that the weights are always vertical, then we know that anything that's going to be perpendicular to those weights is going to be a horizontal line. Okay. And so that basically means that whenever you compute the moment arm for a vertical force, it's always going to be a horizontal distance. Okay. Okay. So I'll do one kind of example here, just very carefully, and then all the others are going to, follow from that. Okay. So let's compute the moment that's going to be, that's resulting from W1. Okay. Okay. And so W1, let me go ahead and draw the figure again. So here is our shoulder joint. Here is the arm segment. And so we know this segment has a length of L1 going in that direction. We know this angle here is theta 1. And we know the weight is coming down W1 just like that. Okay. All right. And so the moment arm that we want to compute, is because we know W1 is a weight, is going to be this horizontal distance right here. Okay. All right. And so that's what we want to compute. And so we're not given this horizontal distance directly within the problem, and so we're going to have to compute it based on what we're given. But we can just use simple trigonometry to do this. Okay. And so let me draw this. And so let me continue to use blue right here. And so if we know that the shoulder joint is down here, okay. If we draw this triangle, and so if we draw a triangle to the hypotenuse of the triangle is going to go straight from the joint to where the weight is acting. Okay. Got to continue that down. Okay. Okay. And so let me kind of extract this triangle here. Okay. So all I did was I drew a triangle with the hypotenuse going up to where W1 is acting. Okay. Right. We know the angle at the bottom of this triangle. So we know that this angle is theta 1. And we know the hypotenuse of this triangle because we know that W1 is acting halfway up of L1. And so we know that this hypotenuse is actually going to be L1 divided by 2. Okay. All right. And so, based on this triangle, the fact that we know the hypotenuse and the fact that, we know the angle, we can compute, the length of this edge of the triangle right here. Okay. And so if we use our trigonometric rules, SOHCAHTOA, we know that this edge here is adjacent to that angle. And so to compute its length, then we take the length of the hypotenuse, which is L1 divided by 2. Okay. And since it's the adjacent edge, we're going to multiply it by the cosine of that angle. Okay. And so the moment arm for W1 is going to be L1 divided by 2 multiplied by cosine, okay? And so if we combine this together, okay, if we combine this together, then the moment, as we shown earlier, is the magnitude of the force, which is W1, multiplied by its corresponding moment arm, which is L1 divided by 2 times cosine theta 1. Okay. All right. And so that is the moment from W1. Okay. Let me show this for W2, just because W2 is a little bit of a unique case. And then we'll talk about FM, and then we'll solve the problem from there. Okay. Let me switch my color back. All right, so W2. And so W2 is a little bit more unique compared to W1. Okay, so let me go ahead and draw the figure for it. And by the way, what I'm doing right now in drawing a figure for every single force, this is not, I know you might think that this is kind of a waste of time. And so, because it takes a lot of space, but you can see here that, when you draw the figure for every single force, it makes it very clear what the moment arm is. So don't be afraid to do this on the exam too, because, it can be difficult. And I think this is the most common mistake I see people making is, not knowing what the moment arm is and, not getting the moment equation right, okay? All right, so W2. And so we know that we have the upper arm segment here, okay? And then and we have the other arm segment right here, okay? We know that W2 is acting at this location right here, okay? It's going vertically down. And then to compute its moment arm, we need the geometric information. So we know that this length right here is L1. This total length right here is L2. This one's theta 1. And this angle right here is theta 2. Okay. Okay, and so let's go ahead and follow the same logic we did in the previous problem, and then use this to compute the moment arm for W2. Okay. All right, and so just like the previous W1, we know that W2 here is a weight, and so if we kind of trace this downwards, okay, right? I'm just extending the arrow. Then we know that the moment arm that we seek is this total distance right here. Okay. All right, and so what's different about this one is that to compute this total distance, we're actually going to need two triangles because we have two different arm angles. Okay, and so our first triangle will be this one right here. Okay, so very similar to the last one. Okay, but that only covers up until we get to the elbow joint, because once we get to the elbow joint, the angle of the lower arm is different from the upper arm. Okay. And so the second triangle that we need is actually going to be this one right here, okay? And so we have two triangles, and so let me go ahead and draw them out here just for the sake of, for clarity. And so the first triangle is going to have a hypotenuse of L1. It's going to have an angle of theta 1, and then our other triangle here, I'm trying to draw this so that they actually look different. So actually, let me go ahead and redraw that for a second. I know this is a little bit exaggerated, but it's a bit easier to look at this way. Okay. And then this hypotenuse here is only going to be L2 divided by 2, because just like W1, W2 here is going to act halfway up the lower arm. Okay. Okay, and so the total horizontal distance that we want is going to be the sum of the adjacent edges of these two triangles. Okay, so we have this edge right here, and then this edge right here. Okay, so let's go ahead and add up those distances. And so the bottom one here, this is going to be L1 multiplied by cosine theta 1. Okay, and then similarly for the upper triangle, we have the hypotenuse L2 divided by 2 times cosine theta 2. Okay. And so the total distance is just going to be these two added together. And so we're going to have L1 cosine theta 1 plus L2 divided by 2 cosine theta 2. Okay. And so if that's the moment arm, then we are going to multiply this by the magnitude of W2, and that's going to give us the the force. Okay. All right, or the moment, excuse me. So total moment. The total moment for this case is going to be W2 multiplied by the sum of these two quantities. So L1 cosine theta 1 plus L2 divided by 2 cosine theta 2. All right. Okay. So I'm not going to do the moment for W because W kind of follows the same logic here for W2, but you can see here that sometimes to get the exact moment arm, you're going to have to take the sum of multiple things. Okay, so don't be afraid to do something like this, especially when it's warranted. Okay. Okay. All right, and so that's the moment arms for the weights. Let's go ahead and do the moment arm for the muscle force because this one is the logic for this one is a little bit unique. Okay. All right, and so once again, I'm going to draw the arm. Okay. And then we have Fm acting on the arm, theta m. And then we have this distance right here, Lm. Okay. Okay, and so I think there's been some confusion, and I think this is partially my fault. Just I think because I did an example where I kind of broke this Fm up into components. But typically when you're looking at you're computing the moment from a muscle force, you're only going to have just one component. Okay. And you can't really, and so the logic for this is going to be a little bit different than the weights, just because this direction FM is a little bit oblique, and so it's not really vertical like the other ones. Okay. Okay. And so if you were to kind of follow the same logic as before, what you would have to do is you would kind of have to draw a triangle here. Okay. Okay. So this is kind of the triangle that you would compute. Okay. Where this is a right angle right here, and you would somehow have to compute, the length of this, the length of this side of the triangle right here. Okay. Which you can do, it's actually not that difficult. So it's actually just a different way of looking at it. And so if you were to do that, we know the hypotenuse of this triangle. The hypotenuse of this triangle is Lm, and the angle of that triangle is theta m. Okay. And so the length that we actually want here is actually going to be the opposite side. Okay. And so the opposite side of this triangle is going to be sine Lm sine of theta m. Okay. Okay. So actually, that wasn't that bad. And so if you wanted to look at it in this way, then that would be another way that you can do it. Okay. And so knowing that the perpendicular distance is Lm sine of theta m, then the total moment in this case is Fm Lm sine of theta m. Okay. Okay, so that's actually a valid way to do it, and so you learn something new every day, and so I kind of learned how to actually apply that that perpendicular distance. Okay. Okay. All right. But the way I think the way that I taught in the class, and maybe this has been a little bit confusing for people, is that what I do is I break up the components for FM into one that is along the LM direction and one that's perpendicular to one. Okay. Okay. And so let me go ahead and create a zoomed in picture of this. Okay, so this is the joint right here. This is the segment. So this here is FM, and that's the that's the direction that we have drawn it in the figure. And so to break this up into its two components, and this distance right here being LM, that means we have one component that's parallel to that. Okay. And so the component that's parallel to that is FM cosine of theta m. And then we have a component that is perpendicular to that, and that's FM sine of theta m. Okay. All right, so what's unique about these two components here? And so we know that Fm sine of theta m, that's definitely going to contribute to the moment because it's pointing away from the joint, and it has a moment arm of Lm. Okay, the parallel component Fm cosine of theta m, that's pointed directly at the joint itself. Okay, and so this component right here is not going to contribute to the moment because it's pointed right at the joint. Okay. Okay. And so we don't worry about that one. And so the only component that we can worry about is Fm sine of theta m. Okay. And then its moment will be computed by multiplying this by the perpendicular distance. Okay. And so the perpendicular distance in this case is exactly Lm. And so we get a moment of Fm sine theta m Lm. Okay. And so that's exactly kind of what we got before. Right. And so both of these, let me go ahead and cross this out. Okay. And so both of these methods here are going to work. It's just kind of how you interpret it, right? And so, of course, I'm spending a lot of time on this review, talking about moment arms, but I think, that's probably the trickiest part of these problems and the one that, that I think a lot of people seem to be struggling with. Okay. Okay, and so of course the last thing that we need here is determining the sign of these moments. Okay? And so we're going to use the same convention as we did before, and so we're going to use a positive sign for counterclockwise moments, and then a negative sign for clockwise moments. Okay, and so relative to the joint right here, we can see that FM, if we kind of trace this around, is going to have a counterclockwise moment because it's going in the opposite direction of a clock hand. Okay. Meanwhile, all the weights, if we kind of follow them around, because they're taking place on the right side of the joint and they're pointing downwards, that those are going to be a clockwise moment. Okay. All right. And so let's go ahead and put this all together. So let's go ahead and sum up all the moments around the joint. Okay. And so let's go ahead and start with the muscle force. And so for the muscle force, we know that it's a counterclockwise moment, so it's going to be positive. So we have FM, LM, sine of theta M. Okay. And then we have the moments from all the weights. And so all the weights are going to be negative because they're they're clockwise moments. And then we're going to compute their values based on the logic that we kind of just went over. Okay, so let's start with W1. So we did W1. And so we have W1, L1 divided by 2 cosine of theta 1. Okay. Then we have W2 multiplied by its moment arm. So that's L1 cosine theta 1 plus L2 divided by 2 cosine theta 2. And then lastly, we have the weight at the end of the arm. So this is one that we didn't explicitly compute, but it follows the same logic. And so we have W times L1 cosine theta 1 plus L2 cosine theta 2. And all that's going to be equal to 0. Okay. Because this is a static problem. Okay. All right, and so let's go ahead and solve this equation for FM. Okay, and so FM is equal to, okay, all of the minus sign entries here, we're going to move to the right-hand side of the equation. So we have W1, L1 divided by 2 cosine theta 1 plus W2, L1 cosine theta 1 plus L2 divided by 2 cosine theta 2 plus W L1 cosine theta 1 plus L2 cosine theta 2. Okay. And then we divide by the moment arm for FM, so that's LM sine of theta M. Okay. And so we punch in all the numbers. Just as a reminder, all the numbers are given up here. Okay, so it's a lot to punch in. And so, for these types of problems, remember to kind of punch in really carefully. And so we get 13651.54 newtons. Okay. All right, so that's a very long very long process, but hopefully that makes it clear how I kind of think about these problems and how I compute the moment. Okay. All right, and so the last thing we're going to do here is we're going to compute the joint reaction forces, and to do that we're going to sum up the forces in the x and y directions. Okay. Okay. But for this one, there's a little bit of a complication too, and so I want to make sure I talk about this as well. Okay. And so to do this, let me go ahead and draw the lower arm again, or the upper arm, excuse me. Okay, so we know the upper arm is angled with respect to theta 1. Okay, so that's with respect to the horizontal. Okay, and so I'm underlining horizontal here because that's that's the important distinction, right? Because remember, whenever you have an angle, it's an angle basically tells you the relative orientation between two different lines. And so, I think a lot of times when we think of an angle, we think of just, that's the angle that a single line makes, right? But it's more than that. And so the angle, whenever we're given angle, it's always the relative position between two lines, okay? And so this theta one here, is the angle that this arm makes, right? And so that's one of the lines that we're measuring. And the other one, which is kind of implicit, oftentimes we don't even think about it. The other one is going to be with respect to a horizontal line. Okay, so that's going to be really important. Especially once we start to talk about the next thing, which is the muscle force. Okay, so the muscle force we know is acting in that direction right there. Okay. And then the angle that we're given for the muscle force is theta m. And so this theta m, so theta m here is the angle that Fm makes with respect to the arm, not the horizontal. Okay. Okay. Right. So you have to be careful with that. And so, you have to, whenever you're given an angle in a problem, you have to ask yourself, what is what direction is this pointing in? And what are the two lines that are, being measured with this angle? Okay. And so we have to be careful here because I think normally, when we do something like we sum the forces in the x direction, okay, what we're kind of accustomed to doing, and it's kind of muscle reflex, and so I do this too, is that we just take the cosine of that angle, okay? And so let's say we have a force, we take the cosine of an angle, and we know that just by reflex, just by what we've been taught, that's the horizontal component. Okay? But when we do something like this is always under the assumption that this theta here is with respect to the horizontal. Okay. Okay. Okay, and so if you're going to use this sine cosine convention for the sum of the forces in the x and y, you have to kind of be careful of the angle that you're using, and you want to make sure that you're always using an angle with respect to the horizontal. Okay, so let me give you a very quick example here. And so let's go ahead and sum the forces in the x direction for this for this figure here. Okay. And I'm picking x because the weights don't make any contribution to the x direction because they're all pointing downwards. Okay. Okay. So in the x direction we have two forces, and so first thing we have is the joint reaction force in the x direction. So that's Jx. Okay. And so the next thing that we need is the muscle force. Okay. And so the muscle force, just visually we can see is pointing to the left, and so we think it's going to be negative. But the question is, what angle do we use for this, for this case here? Okay, and it's really tricky because the angle that we're given here is, on the opposite side of kind of what we normally expect. Okay, okay. And so let me draw it like this. And so, if we consider the arm here as a vector, okay, then we know that the vector here is goes from kind of the origin. We're assuming the joint here is the origin and points upwards, and it rotates counterclockwise by an angle of theta 1. Okay, and so if we kind of imagine that all vectors kind of start at the x-axis, okay, by the purely horizontal line, then in order to get into any position, we can have a counterclockwise rotation. Okay. Okay. The FM, on the other hand, is pointed the other direction. Okay. And of course, we know that the angle is given is with respect to the arm itself. Okay. But let's think about it like this. And so, instead of, saying that the angle right here is theta m, let's instead say that, okay, one way that we can get FM right here is that if we start with a vector that's parallel to the arm, and so it's parallel to L1, and then we rotate it counterclockwise this way, okay? Right, and so the angle that we're looking at now is not kind of the small angle here. It's kind of this big, kind of obtuse angle, okay? Okay, and so this represents the counterclockwise rotation of FM away from the arm, okay? Okay, and so the reason I'm doing this is because, I want to stay consistent with the kind of the rotation angles that we're considering here, okay? And so we know that theta 1, the way that we define theta 1 is as a counterclockwise rotation away from the horizontal, okay? And so the muscle attachment angle I want to define as a counterclockwise rotation away from some axis, okay? All right, and so, now that we've defined the angle this way, we can compute what this angle is, okay? And so this angle right here, may not be clear at first, but, we know that this angle is theta m, okay? And we know that if we made a full kind of rotation here, or full half rotation, and so if we continue all the way down here, that would be 180 degrees, right? And so if we rotate 180 degrees, we know that we just make an about face. And so we just kind of reverse our direction, okay? And so knowing that a full half rotation is 180 degrees, and we know that the angle that's given to us there is theta m, that means the angle that we want, which is the counterclockwise angle, okay? Oops. The counterclockwise angle that we want here is going to be 180 minus theta m. Okay. Okay. All right. And so this is kind of a long path to get here, but now that we've kind of defined these angles, okay, in this way, we can see that the FM is going to make a total rotation of the sum of these two angles, okay? Okay, so that's the total kind of rotation that that FM is going to make, okay? All right, and so that was kind of a very, very long process, and so it's all going to justify in just one step here. Okay, so now if we take the sum of the forces in the x direction, We know that we're going to have the joint reaction force in the x direction, Jx. And then we're going to add the horizontal component of this rotation here. Okay, so we're going to have Fm cosine, okay, of theta 1 plus 180 minus theta m, and this is going to equal to 0. Okay. All right. And so we're kind of back to using our typical form here for cosine, right? Because what was our conditions before? And so our condition to using cosine before, oh, I erased it, but the condition of using this is that, this angle right here, this angle is the angle that the vector makes compared to the horizontal, okay? Okay. Because remember, if we start at the horizontal line, first we rotate theta 1, and then from there we rotate 180 minus theta m. Okay, so it's kind of a total kind of rotation like that. Okay, and so using that form, we're able to do that. Okay. All right, and so from here, now that we've kind of justified this angle here, we can solve for Jx. Okay, so Jx is going to be minus Fm cosine theta 1 plus 180 minus theta m. Okay, so we plug in the numbers for this. We get 12828.25 newtons. Okay, and then we're going to do the same thing from the y direction. So sum of the forces in the y direction. This is equal to Jy plus Fm. Since this is in the y direction, we're going to take the sine of the angle. Okay, so Fm sine theta 1 plus 180 minus theta m. And then here we need to subtract all our weights too. So minus W, minus W1, minus W2. All that's going to be equal to 0. Okay. So we solve this equation for Jy. So Jy in this case is going to be W plus W1 plus W2 minus Fm sine of theta 1 plus 180 minus theta m. Okay. We plug in the numbers for this. That should be negative. We should get a negative 5504. Or excuse me, no, this is positive. Yeah, this is going to be positive too. Positive 5504.1 newtons. Okay. All right, and so that's the example. And so I wanted to do this one for this review because I know that the homework solutions for this are quite sparse, and so I kind of just skip a lot of steps. I skip a lot of my logic, but hopefully by looking at this kind of very detailed view of this example, you can kind of see a lot of my thought processes and how I determine each of the terms in the moment equation and the force equation. Okay. All right. And so, that's been about 45 minutes for this review session. And so, I think that's good. I don't want to make it too long, right? And so, hopefully this was helpful for you. As you're kind of, going about doing your exam practice problems, you can follow this kind of same logic. I know I kind of went through everything in excruciating detail here, but, you don't have to cover everything, in that much detail. But what I'm hoping for is that seeing all this detail will kind of help you kind of work out these problems on the homeworks and of course on the exam as well. Okay, so remember the key points here are to remember what the moment arms represent and how to properly compute them for each of the moment or for each of the forces, and then what do each of the angles represent and how do we utilize that in our force equation. Okay. All right, and so as always, if you have any further questions, please feel free to contact me. I'm always open to answer questions by email. Or if you want to make an appointment, I'm always happy to do that. Okay. And so the exam is going to be this Thursday. So remember, come with your writing utensil, come with your cheat sheet and your calculator. Okay. And I guess I'll see you guys all on Thursday.